Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hi students, so we continue our discussion of semiconductor devices and see, one book you can read is Concepts of Physics by Professor H.C. Verma. As you know, I already discussed this last time. Professor H.C. Verma has been given the Padma Shri. That's not why I'm asking you to read. I want all of you to be on track for the Padma Shri. That's why I'm asking you to read. So this is the chapter 45. Okay. So last time we discussed semiconductor devices. I was very lucky to be taught semiconductor devices by Professor G.K. By Professor K.N. Bhatt. Professor K.N. Bhatt was our teacher, but I don't remember everything in semiconductor devices. I learned it long time ago, but I'll tell you what I did learn. Okay, typically there are many ideas that you should know in semiconductors. And the first and most important idea is deals with this idea of bias. So I'm going to do a quick revision of what we learned last time. Okay, so now a semiconductor has you can change its behavior by changing the doping impurity. Okay, so semiconductor is a very pure element. Firstly, you have to when they make silicon for semiconductors, they really purify it. They go to it's done in a furnace, and then they kind of there is a very big process for it. They make it crystalline silicon of the highest purity, and then into that crystalline silicon. So it's like a grid. You can think of the silicon as an infinite grid of silicon atoms. Now into those so now that high purity silicon is then cut into at small micron levels, it is cut, precisely cut, with very you can the amount of the wafers into wafers, and those wafers are extremely pure. Now that wafer, right, is then doped. Okay, now then there is metal added on top of the doping. Okay, and then the wire is drawn from that metal that gets added, so that and then that it conducts. You have a chip, and then you have like pins in the chip, etc. Right? So those are the mechanisms through which data gets passed in and out of a semiconductor chip. Right? So there is metal which then connects into the wafer, which is doped, okay, into silicon wafer, which is doped. So that's precisely how it works, and we saw a picture of it, or at least a simple representation of it, right? So now the type of doping, right? If you use a N-type doping, right, or a P-type doping. Now, P-type is deficient in electrons, okay, and N-type has an excess of electrons. So, phosphorus or arsenic typically is used to increase the, makes conduction of electrons because there is more electrons. Okay, so whether arsenic is, I think, 3, phosphorus is 5. Now, if you have, or actually arsenic is also 5. So, but if you use aluminum is 3. Okay, phosphorus is 5. So pentavalent impurity, right? Phosphorus is a pentavalent impurity, right? Phosphorus pentoxide P2O5, right? So it forms bonds using of that type, right? So pentavalent impurity like phosphorus makes conduction electrons much higher than the whole concentration. And these are N-type semiconductors. N-type semiconductors has a pentavalent impurity that is embedded into that the silicon is doped with. Now, a p-type impurity, on the other hand, is rich in holes. Okay, so now typically what happens is the impurity levels are created slightly below the conduction band, and are occupied by the extra electrons attached to the impurity ions. Okay, now, due to thermal energy, a large number of them go to the conduction band. Okay, and this increasing the number of electrons, Ne. Okay, now those are free to travel. Those electrons are free to travel. Those that are in the valence band, they don't travel, right? The conduction band electrons, they can little bit move around. Okay, so there is an intrinsic concentration, and this is of the order of 10 to the power of 10 per centimeter cube. The impurity electrons for parts per million type doping could be around 10 to the power of 16. Okay, so that's the number of electrons that come into play. Now, the increased number of electron concentration enhances the rate of recombination. So, what is recombination? So, now you have a p-type and you have an n-type, right? So, now you have these two layered like this, right? So, I think I did show you a picture of this picture, right? This is called a p-n junction. You have on the substrate, right? You have an n-type. Then on top of that, you dope it with a p-type. Okay. Then on top of that, you have some metal, and then you have a contact. You draw, you connect this to a wire. The metal contact is connected to a wire, right? Or it's a pin, right? And then that goes to a wire as part of the circuit board, right? But the substrate itself also sits on metal, but the semiconductor is an n-type here, and then there is a partial p-type on top of it. Okay, so now you have a p-n junction. Okay, so that is how it looks. Okay, or you can think of it in that sense. Okay, now so you increase the number of hole concentration enhances the rate of recombination of electron holes, and the electron concentration further reduces. Ne times Nh equals Ni square. Okay. Through conduction, electron concentration or hole concentration changes due to doping. Okay, so greater the doping, the average charge density remains zero in the material. This is because only neutral atoms are doped. Okay, so there is a net charge, and then there is a dynamic equilibrium between the p and the n. Okay, now what happens in between? So when an electric field is applied in the semiconductor, so find you apply a field, you apply a field here and a field there. Okay, so now which side is positive versus which side is negative is right now I'm not telling you. Okay, we will discuss that later. Okay, now but then when you apply an electric field, the electrons and holes, they move systematically, and then there is a current generated, not all the time, under certain circumstances. Now there are actually two currents. Okay, and we will discuss these two currents after first understanding how this recombination process happens, right? Electrons on one side, electron rich part on one side, hole rich part on the other side, and then there is a dynamic equilibrium between the electron part and the hole part. Okay, now the n type is rich in electrons, p type is rich in holes. Now there is what is called a drift current. The electrons drift slowly towards the holes. Okay, now after that drift, right? So okay, so people from this side go to that side, people from that side come to this side, kind of thing. Okay, think of it that way. Okay? So you have two villages. One village is of a certain type, the other village is the other type. Little bit people from this village go there, little bit people from that village go there. Now in between, after some time, in between there is what is called a depletion layer is formed. Okay, so that depletion layer, right? Eventually, what happens is there's a little bit of neutrality on either side, and the depletion layer has a associated electric field. There is an inbuilt electric field in the depletion layer, which kind of causes a little bit of a barrier. Okay, so you have to overcome that electric field to go from one side to another. Okay, now which way you are placed, right? So now if you have this kind of a situation, this is the starting point. A lot of N type has more electrons, P type has more holes. Now, after the depletion layer is created, you have a positive, positive um, um, positively charged side and a negatively charged side, and there is a inbuilt electric field here. Now, when you apply a voltage, right, you have to overcome this electric field, and so that is what this is all about. Okay, so if due to the depletion layer, there's a difference in voltage or potential of two layers, so there exists a barrier voltage. Okay, so this barrier voltage, right, up to this barrier voltage, nothing will happen, whether it's this way or that way, whether you connect the positive to the positive or positive to the negative. This depletion voltage, if you don't overcome, it will just keep everything in a block. It will block everything. Okay, so now that once you cross that depletion voltage, if you apply a higher voltage than this barrier voltage that exists on the depletion layer, then the junction will start working. And when we say working, what do we mean? It will conduct. Okay, it will conduct, meaning there will be a current. Okay, so a semiconductor below this with very small voltages acts as an insulator because of this depletion layer. Okay, so there is that inbuilt depletion layer. It kind of builds a barrier. Hey, you can't go to that village. Think of it like Romeo and Juliet, right? So, so that is the idea there. Okay, so you have this depletion layer, and then you have to overcome that electric field caused by the depletion layer. Okay, so the depletion layer forms in between the two sides of the junction, PN junction. We showed the PN junction here, if you remember, N type, P type. Then you can then connect a wire from here to there and form a full circuit, right? So that's how it works. So this is how you connect a PN junction. Okay, so this is what we did last time. Okay, so now today we are going to reintroduce some of the other ideas that we need to introduce. So let me share today's slides. All right. So now, so I've little bit revised what we did in the previous lecture. Okay. So now I'm going to connect the dots, or not the dots. I'm going to connect the positive and the negative terminals of this new device that we've made called a PN junction to a battery. Why? Because I want to now overcome this depletion layer. Now, so as we said, there is the P, there is the N, and then there is, see, this is just that figure a little bit turned upside down. There is the metal contact, there's the P, right? And then there is the base, which is also metal. In between, there's a P and N, right? So now, between here and here, this is N-rich, T-rich, electron-rich, hole-rich. Hole is just, it has, the conduction band has spots. It's empty, and it has spots for, So now here, I put you have this depletion layer here between the two sides, right? And then there is a electric field between the depletion layer which keeps these two separately, right? So if you dope it with pentavalent phosphorus, you get N type. If you dope it with, say, aluminum, you get P type, right? So because of a sharp concentration gradient at the junction, holes and electrons diffuse across the junction and combine to make a region carrier free. So here there is a field, but there are no carriers. This region is the depletion layer, as we discussed. Okay. Now the electrons drift towards the holes, or the holes drift towards the electrons. So now you end up with two types of current. One is a diffusion current and the other is a drift current. Okay. The drift current is caused by thermal heating. Okay. Then there is the diffusion current, which which is also caused, and it is because of the recombination of because of the concentration difference, then recombination. So these two currents, but in between there is this potential barrier which is created by the depletion layer, right? So now this to overcome this potential barrier is very, very difficult, So as a result, you have this little bit of a wall in between, and that little bit of a wall is a potential wall. There's a potential barrier between the positive charge appears in the depletion layer on the N side. Remember that. So on the N side, you have positive charge. So the field is like this, is in this direction, from the plus to the minus, right? Remember, on this side, you have more pluses because the electrons get pushed into a soft part, okay, into the other side of it. So you have more concentration of electrons on one part, and then you have the plus side, and then you have the minus side, and then there is a place in the middle which has neither E nor H. Okay, but there is a field in between. Now, so to overcome this, you have to apply a voltage. Okay. Now that is what we are now next going to discuss. Now the potential of the depletion layer, is so the basically there are two parts to it. There is this x1, then there is this x2. Okay. X1 is the negative side, x2 is the positive side. Okay. Now x1 plus x2 is the total width of the depletion layer. Okay. The width of the depletion layer is, if you say it is x and y, right? So then you can calculate, right, P1 x1 by 2 epsilon, right? And P1 y1 by 2 epsilon. And then P1 difference x2 minus y by 2 epsilon. So there are three different E1 plus E2 plus E3, three different potentials. Okay. Therefore, that leads to the net electric field, okay, which is across these electric field 1, electric field 2, like that. Okay. So there are three different potentials. Therefore, you end up with three different fields. This side, there is this kind of a negative field, right? This side, there is this kind of a field, right? So you end up with two different fields. All right. And therefore, your net field, right, is a sum total of these three different fields. Now, you integrate these three fields, right, and then you will end up with the total electric area. So now dV by dx is equal to E, right, and E is P2 times x by epsilon, or rho 2 times x divided by epsilon, right? Rho is the concentration, right? Therefore, using that, you can now get the when you do the integration, you will end up with x square by 2. Okay, so when you integrate x dx, you will end up with x square by 2, which is the potential. So you will end up with a little bit of a polynomialistic curve. V versus x will be somewhat like a polynomialistic curve. Okay, so now, but then it is only over that short range. Okay, so now it will be some kind of polynomialistic curve in these short ranges. Okay, x1 between x1 and x2. Okay, so in that phase, somewhat of a polynomialistic curve, but beyond that, it will be a constant. Okay, so this is what sets up the potential barrier. Now, when you forward bias, what does forward bias mean? You connect the P side to the positive of the battery. Okay, forward bias means you connect the P side to the positive of the battery and the N side to the negative of the battery. So now here you are when you forward bias, what you do is you try to make the conductor flow along the grain. Okay, think of forward bias as not going against the grain of the PN junction. P to the positive, N to the negative is forward bias. Okay, now then it with very small amount of potential you will overcome the barrier, potential barrier. Okay, so just with a small potential you will be able to overcome the barrier, and the semiconductor will start to conduct, and it will have a inbuilt resistance. Okay, so that's what happens. The barrier height, the depletion, when you apply that voltage, the depletion layer will shrink. Okay, so there will be a normal depletion layer. When you apply a voltage, depletion layer will shrink and the diffusion current will increase. Diffusion current is the normal current. Okay, now the diffusion current will increase, so it goes this way, and the drift current will stay the same. Drift is against the grain due to heat, right? So the diffusion current will increase, and that will increase corresponding to the voltage you apply. I versus V will be in the straight line region of the curve. Greater the potential apply, more the current will flow. So it will be like a resistor. It will behave a little bit like a resistor, or you could even say it's like a short. Okay, but below a particular voltage, no current flows. Note that is because the potential barrier in the PN junction, inbuilt in the PN junction, created by the depletion layer. So the width of the depletion layer will shrink in forward biasing. Okay, the opposite is true in reverse biasing. Okay, so let's do a quick quiz. The potential difference between A and B, right? So in this case, so let me tell you, the short line, this is the representation of a diode. A diode is just a PN junction. Okay, now the straight line represents the N side. This represents the P side. Okay, now when in the figure below, potential difference between A and B is, okay, so now this is a very simple thing. This is he's asking you if you understand the difference between forward and reverse bias, right? So is this forward bias? Yes. Why is this forward bias? Because the positive is connected to the positive of the P. This is the P and the straight line is the N, right? So the N is connected to the negative, right? So now this is going to behave just like a short. Okay, the potential difference between A and B will be what? So now if you just make this a short, right, then 10 kilo ohms, and then this is 10 and 10. So the net of 10 and 10 will be 5, and this 10 is 10, right? Therefore, it's 15. So 30 will divide as 20 across this, and 10 across this, 10 volts across this. So it will, the 30 volts will divide as 20 across the 10 kilo ohms, and then 10 across the 10 plus 10 in parallel. So it will end up having 10 volts across AB, 3. Okay. So the important idea here is that the diode is going to act as a short. That's all they want from you, okay, for this question. A quick quiz. Okay. Now, which of the following represents a forward biased circuit? So here 0, here -2. So the higher voltage is connected to this. So that's a forward bias, right? In this case, -4 and -3, -4 is lower. So this is reverse biased. -2 and +2, this is also reverse biased. 3 volts and 5 volts, 5 is greater. So this is also reverse biased. Only this is forward biased. Positive on anode is a forward bias. What he's trying to make sure is you understand that the negative, if you say negative, doesn't mean it's negative actually, right? Whichever is higher, you're looking at not absolute potentials, but you're looking at potential difference. So here the potential difference is 0 minus -2 plus 2, right? This is higher than that, right? Water flows from a higher level to a lower level. Doesn't matter where this can be a mountain, it can be even below sea level. Water will flow from higher level to a potential is also just like that. These are merely numbers. 0 and -2 is just conventions that we follow. -4, -3, right? So -4 is lower potential than -3. Only 0 is higher than -2. So only one is forward bias. Okay. Given circuit has two ideal diodes connected as shown in the figure below. The current flowing through resistance R1 will be. Okay. So now a diode, let's discuss this forward bias again, right? Now, a diode is what is called a rectifier. That means that unless you cross that threshold voltage on the other way, right, it only will conduct one way. Normally, a diode is a rectifier. Okay. Now, you can build a circuit which rectifies both ways, but typically a normal diode will only allow conduction one way. So if you had applied an AC current, which is positive one direction, negative the other direction, the diode will cut it. It will conduct only one part of the positive circle, or only one part of the negative circle, okay, based on whether you're forward biased or reverse biased. Okay, so only one part it will conduct, the other part it won't let the current flow. There is condition that will happen, but we'll discuss that in the next class. So during the positive part, it will allow the current to flow, and it will allow the current proportional to, it will follow V equals IR kind of, delta V by delta I equals kind of resistance, like in the linear region of the I versus V curve here. Okay, so that's the point there. Okay, so now if it's an ideal diode, it will behave as a short one way and an open the other way. There's two ideal diodes. The current flowing through the resistance R1 will be, right? So now if it has two ideal diodes, this one's going to be an open circuit, this one's going to be a short. So you have 2 and 2, right? So 10 divided by 4 is 2.5. So the current flowing through R1 will be 2.5. 1. 10 divided by 4, right? Because this one's a open circuit. This one is a short. That's all they want you to understand here. A lot of these problems are just aimed at trying to teach you what forward bias and what reverse bias is. Okay. So now, so once you understand forward bias, reverse bias is a little bit more tricky. It's not that tricky, but it's still worth understanding how these devices behave. A diode is called a rectifier. What does a rectifier mean? It allows current to flow only one way. Okay, and it is an ideal diode will have no resistance, will allow current easily to flow one way. Okay. Typically, it will have a little bit of a resistance. Okay. The other way, it will be typically an open, but under certain circumstances, that open will also break. And I'll show you when that open is going to break. That condition we will discuss right now. Okay. So let's continue our discussion of the diode. Just okay. So so this is the third lecture in this, right? So we already discussed the PN junction as a half rectifier. Okay, so half rectifier means it only allows one way to go. Now, if you want to construct a full wave rectifier, right, it takes us different kind of circuit, and we will discuss that circuit. It's called a 4-quadrant rectifier. So you will connect 4 diodes in a circuit. So let's come to that full wave rectifier later. But first, let's do a quick recap. Depletion layer, right? Holes, P, N holes. And there's a depletion layer in between where there's an electric field, but there's no holes anymore, right? So one can model the charge distribution as constant each region up to a width. So the electric field looks like that, and the voltage field looks like that. The electric field in each region is linear, and the potential variation is quadratic, right? So electric field is linear, the rho is constant, the electric field is linear, and then the voltage is therefore dV by dx equals E. So V equals E dx. When E is linear, this one becomes quadratic if within a range. It's quadratic here, quadratic there, but otherwise it is flat. That is the potential. Okay, so now, and this is roughly the electron energy band diagram, EC and EV. Now, in forward biasing, the depletion width decreases, and the barrier height and the depletion width decreases. Okay? Now, barrier height is a measure of the voltage. Okay? Now, it is the voltage barrier they're talking about. When they speak of barrier, when they talk of depletion, they mean distance. When they talk of barrier, they mean voltage. Okay, so the diffusion current increases non-linearly, but the drift current remains the same always. Drift current is due to thermal reasons. Okay, diffusion current, drift current is due to thermal reasons. Diffusion current is based on the potential you apply, and so that is non-linear because it's a curve. If it was a straight, it in over a short range, it can be thought of as linear, but it is like a curve like that. Okay, so that's why he's saying it increases non-linearly. The I versus V is a curve like that. Okay, so he says it is non-linear. Okay, now in this phase, there is no current at up to a certain voltage. Above a certain voltage, there is current. Okay, now when you reverse bias it, when that means that you connect the negative, the N junction to the positive of the battery, right? When you reverse bias it, when you talk about a half rectifier, under those circumstances, current does not flow. Now, so when you connect an AC source, which is a source like that, right? It is not like a battery with a positive and a negative terminal. AC source is half the time positive, half the time negative, sinusoidal wave, right? The voltage is sinusoidal, right? Half the time one side is positive, half the time the other side is positive. Now, when you connect an AC source, half the time it will conduct, the other half time it will not conduct. So when you do that, you are said to be using the diode as a half wave rectifier. So it rectifies half the time, and the other half the time it doesn't let the current pass. During the second cycle, that is the second half of the cycle, the Diode is in reverse bias. So we talked about forward bias last time, right? So when you connect the P type to the positive, right? So during that phase, it's in forward bias. During the other phase, it is in reverse bias. During the reverse bias, it will not let current to flow through. So that's what he's saying here. Okay. So this is the symbol of the diode. You have a AC voltage during one half of the cycle. During this half of the cycle, positive half of the cycle, it will let the current flow through. During the negative half of the cycle, an ideal diode lets no current flow through. So we just have this part. Okay. So this is a simple half wave rectifier. Okay. Now every diode has a cutoff voltage. Silicon diodes have a cutoff voltage of 0.7. Germanium diodes have 0.3 volts. Below this, the diode does not work. It is a open circuit on either way. Okay. So now the total current is I drift minus I diffusion. The drift works one way. The diffusion is your more like your conduction current. Okay. So the two currents combine to form the total current. So you have a I versus V that looks like this for a diode. Okay. Now there is a particular case called Avalanche Breakdown. Okay. That is this point. So you have this side of it, but if you keep pumping up the voltage, more and more and more voltage, eventually it's just going to give up and it's just going to let all the current flow. Okay. So beyond a very high level of voltage, the reverse also will break down and you will have very high current. That the voltage at which that happens is called avalanche breakdown voltage. The point at which it happens and that point is called avalanche breakdown. A diode which operates in that range of avalanche breakdown is called a Zener diode. It is just a regular diode, I think, or especially slightly differently made, which operates in that avalanche condition. So it's a Zener diode. It's called a Zener diode. Okay. So this is the avalanche breakdown. It's not usually thought, but you must know about these things if you want to do well. Now, in full wave rectification, you have two paths. One set of diode, one path is the forward path, and then you have the other part, which is the reverse path. So you have two positives and then two negative diodes. So then you rectify either way. In one case, it will go through this way. The other case will go through the other way. Okay. So the two diodes are connected in parallel branches with opposite phases of polarity, so that when one is off, the other is on, and vice versa. Okay. Due to this combination, there is full wave rectification is achieved. So when do you want this full wave rectification? Well, you want it under certain circumstances. Most often, full wave rectification is used to convert from AC to DC. Okay, so we will discuss that next time. So full wave rectification. See here, you have this one and that one, right? So you have the input and then you have the output, and so half the time this one is conducting, the other half of the time this one is conducting. So you have this transformer on the other side of the transformer. You have these two diodes. Therefore, you end up with a full wave rectifier. Okay. So and so that is basically how these things are made to work. Okay. So now, as I discussed before in teaching you how those problems work, I discussed the idea behind this for when the diode acts in the forward bias, an ideal diode will act as a short. In reverse bias, it acts as the open, right? That is the ideal diode, but normally it follows these more realistic principles where these diffusion current and drift current, they kind of match up. In reverse bias, the depletion layer will expand. Okay, in forward bias, so if this is the normal when there is no voltage applied, this is the depletion layer. In reverse bias, it will become like this. In forward bias, it will become like that, very short depletion layer. But there will always be a depletion layer. Okay, so now so let's now discuss this new ideas that we have now found, which deal with this you know okay, which now deal with this reverse bias case. Okay? So in reverse bias, there is a long time during which there's a not long time. There's as you apply more and more voltage, it's typically an open. It will not let current flow through up to a certain point. At that point, it will allow all the current to flow through. That is called avalanche breakdown. Now, in reverse bias, the p-n junction diode doesn't work. It's very small amount of current flows through. It's in microamperes, very, very little current. In reverse bias, the p side is going to be negative, right? Current that flows is due to minority charge carriers, that is holes through the n side and electrons through the p side. Okay, normally in a n side, what will you have? You will have electrons, but there will be a few very, very small impurities. They are what are called minority charge carriers. Those impurities will cause little bit of flow, but otherwise you will not get, if you are perfect, if you made a perfect diode, you won't get anything. Okay, now here we have applied this voltage, and now we have reverse biased. Now at this point, this is the avalanche breakdown point. At this point, it starts suddenly conducting, and very quickly it just, all the current comes at this, from when you increase the voltage above this point. This is like all these, they used to talk about the strong silent type, like Amitabh Bachchan, right? Amitabh Bachchan was always used to be this angry young man, strong, silent type. But then there would be this final scene when Amitabh Bachchan would break down and he would start crying. Till then, he will not say much. He will only be fighting, or only a man of few words. Angry young man, few words, right? Now, but in the end of the movie, he will start crying, and then you will have avalanche breakdown to be like this. Okay, so the I versus V, you will have, at a certain point, when you increase the voltage beyond that point, the current will start flowing, and start flowing very, very quickly. Okay, so that is how avalanche breakdown happens. Speed increases, they collide with the valence electrons, and the bonds are all broken. Everything breaks. Okay, so that's avalanche breakdown. Occurs in a p-n junction, which is reverse biased, and avalanche breakdown usually occurs when you apply a very high reverse bias voltage across the diode, but it's in the reverse bias. Okay, obviously it's higher than the Zener breakdown voltage, which is called VZ. When you apply voltage higher than that Zener breakdown voltage, VZ, then start flowing rapidly. So now this is the knee of that curve. When you increase it here, you will have a lot of current. So this is forward bias, right? This side is forward bias. This side is the reverse bias. You're applying a negative voltage, right? And then, so beyond that knee of that Zener, you have avalanche breakdown. Okay. So now this point from here on this side, you will have avalanche breakdown. Okay. So there are two types of breakdown: Zener breakdown and avalanche breakdown. Okay. So these are the two points, and the Zener diode is always operated in reverse bias, and then it is used to, it is essentially used as a voltage regulator. Okay, so now what is a voltage regulator? Suddenly you have a spike in your voltage, like that, your lights go up in your house, right? So to modulate that, they use the Zener diode in, for instance, for your laptop. You don't want your laptop to break down because sudden surge in the voltage, right? So to temper that, they have the Zener diode in the circuit. Zener diode will then let all the current, high voltage, it will absorb all the current. It will let all the current flow through. Okay, so and then it will of course heat up and all that, but that's a different story altogether. So that is a Zener diode or Zener it acts as a switch. Okay, so Zener breakdown happens, therefore you have what is a Zener diode. Okay, so now, and that is the reverse bias condition. So today I am going to stop a little bit early, few minutes early, so that you guys can try to understand a little bit about this Zener diode, and then we will continue discussion with the Zener diode next class. Okay, and we will then discuss how voltage regulators are built, and photodiodes as well, where there is a light. When light is shined on a diode, it then conducts. And then you have, of course, the LED light emitting diode, which you use today in the the lights that we have in our home, right? They use a LED, right? LED lighting, right? Very, very important, ongoing, given all that has happened. Previously, we were using tungsten, now LED, right? So that also we will discuss in all this in the next class. Okay, so LED is the reverse of this photodiode. The LED emits current and emits light when you apply a voltage to it. And then we will discuss, of course, the solar panel. Solar panel also has the PN junction in some ways. Okay, so we will discuss all this. Is electrons, when light falls on it, there is a current induced. Okay, so we will discuss that as well, all of it in the next class. I felt there's too much material, the relationship of LEDs and diodes and the solar panel. I would keep that discussion for next week. But until then, please do some problems, download our app, go to play.google.com, look for Ramanujan or Sushruta, com.JnanaMarga.Sushruta or com.JnanaMarga.Ramanujan. Download the app and do some problems. Assessment. Use the assessment module that we have built. We have built it for all of you students so that you can succeed in this. So with that, I'm going to stop and then we will continue again next class. If it's Sunday morning, you are here with me for physics. There's also Professor Tiwariji's lectures. Please attend all of them very, very regularly. They are extremely important lectures. Unless you do very well in physics and chemistry, you're not going to be either an engineer or a doctor. Will you take it from me? You have to learn this material very, very well. You have to take interest in all this. Must study. Studying builds your ability to do well with whatever else you do and whatever else you take up in life, builds your intellectual capacity. You must build up your intellectual capacity to learn, capacity to understand, capacity to think. All this is built, in your class 11, class 12 by studying hard, learning what you need to learn well, reading the textbook, solving the problems, and listening, of course, to lectures and then attempting the material. Okay? You learn more and more, look at more and more problems, then you build your strength and your capability. So with that, I'm going to stop today. But I hope you did understand all that I said with respect to the semiconductors and the diode and everything, right? So with that, I'm going to stop and we will discuss this again next class. With that, bye.